On your mixture of experts or MOE model training, your expert matmos are running in BF16 on a B200. That GPU has absurd FP8 and NVFP4 throughput. So why aren't you using it? Because the first time you try mixed precision experts, it makes training worse. Let's look at what B200 NVIDIA's 5th gen tensor cores actually offer. BF16, your baseline, FP8, E4, M3. Twice the throughput, half the memory. NVFP4, 4 times the throughput, 3.5 times memory reduction. NVFP4 isn't just 4 bits, it's a 2 level scaling system. Every 16 values share an E4 M3 scale factor. That's fractional precision, not just powers of 2. Then a per tensor FP32 scale normalizes the whole thing. In NVIDIA's reported measurements, NVFP4 achieves 88% lower quantization error than MXFP4's 32 value blocks with power of 2 scales. In a DeepSeek shaped MOE, experts dominate your compute. If you're leaving these tensor cores on the table, you're leaving almost half your hardware idle. So, why doesn't everyone do this? Because FP8 experts isn't one operation, it's a pile of extra work. This isn't a D type flip, it's an overhead plus layout plus stability problem. Quantize weights into a low precision cache, maintain scale factors in the right swizzled layout, quantize activations on the fly, pack metadata so the kernel can run, refresh caches after every optimizer step. Do that naively, and the overhead dominates. You get the memory win, but step time gets eaten by the work around the matmul. That's why people bounce off. They try FP8, it's slower, they go back to BF16. Here's the naive approach. You keep master weights in BF16 for optimizer stability. That's correct. But after every optimizer step, you requantize all expert weights into FP8 caches, recompute scale factors, pack them, swizzle them into MMA friendly layouts. Then you run the forward pass. See the problem? You've created 2 workloads, the optimizer update, then a completely separate requantization pass. The work you added, requant plus scale computation plus packing plus layout transforms, becomes a second workload competing with your actual training compute. This is the classic mixed precision makes training slower failure mode. Let's measure what happens in an expert forward. 1. Dispatch overhead, routing, sorting, grouping metadata. 2. Activation quantization, BF16 to FP8, E4M3, plus computing E8M0 scales per 32 element block. 3. Weight cache refresh. Master weights to FP8 or NVFP4 cache, swizzled for tensor cores. 4. Expert compute. The grouped gems and sway glue, what you actually wanted. 5. Return and scatter. Outputs back, gates applied. If you don't measure these separately, you will lie to yourself about FP8 is faster. The NMOE library is instrumented to make this measurable. Training emits per segment timings into DuckDB. You can view them in NVIS. NVTX ranges let you attribute step time and Nsight. They also use explicit timing tags per segment, so you can see dispatch versus gem versus return versus optimizer without guessing. The right question isn't, did tokens per seconds improve? It's, did expert compute become big enough to pay for quant and cache overhead? You're winning when GEM dominates overhead, not the other way around. Here's something that trips people up. Block scaled FP8 and NVFP4 isn't just smaller numbers, it's spec values plus scale factors, and the memory layout of values and scales is part of the performance contract. The scale format depends on the path. FP8 often uses E8M0 like scales. NVFP4 uses E4M3 scales. On B200, grouped GEM kernels want scales in a specific swizzled MMA friendly layout. Just store scales next to weights is the wrong mental model. NMOE uses a single path strided design, not list of pointers convenience APIs. Scales are first class tensors with kernel expected swizzles baked in. The grouped block scaled path is contiguous and GPU friendly, not pointer chasing. This is what turns FP8 or FP4 from a theoretical throughput number into a real kernel you can hit consistently. Correctness is values plus scales plus layout. Performance is don't break the layout contract. NMOE treats separate cache refresh as a design bug. The fix fold cache refresh into work you're already doing. You already touch expert weights in 2 places, the optimizer update and the dispatch path. During the optimizer update, Don't just write BF16 masters, update masters, and emit the FP8 cache in the same fused path. Refresh isn't a second pass, it's the final write format. During dispatch, do remaining quant, pack, and scale swizzle steps where you already do expert major grouping and metadata building. Pipeline it so overhead hides under compute. The goal isn't zero overhead, not realistic. The goal is no separate refresh everything wall at the end of the step. The FP8 machinery becomes background noise under the expert forward you wanted to run anyway. Even if you fix overhead, stability is the next cliff. Now, here's what breaks first when you add low precision. It's almost always the router. Routers already live on small, noisy gradients, especially in research scale runs. Quantization noise changes the learning signal. And once routing gets slightly worse, you get a runaway feedback loop. Bad routing means fewer tokens per expert. Fewer tokens means worse expert updates. Worse updates mean worse routing. The system doesn't self heal. Cold experts stop getting updates, performance degrades, and low precision makes this failure mode faster and sharper. The trap is responding with 40 knobs to tune: aux loss weight, load balance alpha, router Z loss, expert dropout, capacity factor, jitter noise, knob soup. This isn't a knob soup problem. The NMOE philosophy: keep the surface small, fix root causes instead, make per expert batches hot with RDEP pooling, keep dense and attention stable in BF16, fuse the FP8 machinery so it's not a confounder, instrument router health so you see collapse early. Don't tune your way out of this, fix the architecture. Signals that actually predict collapse. Load entropy, token distribution over experts starts peaking hard. A few experts dominate. Min load starvation. Some experts' token counts trend towards zero for sustained windows, not just one step noise. Load variance trending up. Step to step variance should shrink as training settles, not grow. Gating confidence spikes. Router makes overly confident top case selections. Sharp gates usually correlate with collapse. Per expert batch shrinking. Global batch is constant, but effective per expert batch drops. Routing is degenerating. The meta signal: once starvation persists, it doesn't self heal. You need to see it coming. This is where RDEP pays off again. RDEP pulls tokens across GPUs before expert compute. With 8 GPUs, each expert sees roughly 8 times more tokens per step. Larger per expert batches reduces variance. Less variance means more stable router gradients. Stable gradients mean the feedback loop doesn't run away. RDEP doesn't just fix utilization, it makes routers less fragile, and that's what makes low precision experts actually trainable. So that's the mixed precision story. Let's recap. The promise: FP8 and NVFP4 tensor cores are incredibly fast. Use them. The trap: naive implementations create a second workload. Cache refresh dominates. Router collapses from gradient noise. The fix: fuse cache refresh into optimizer. Emit FP8 as the final write format. Fuse quant into dispatch. Pipeline it where you already touch the data. Track router health, load entropy, starvation, confidence spikes. Use RDEP pooling. Larger batches stabilize everything. The litmus test: when you break down step time, cache refresh should be a rounding error, not a bar. The code is open source and the link is in the description. In the next video, we will do a router stability deep dive, load balancing losses, auxiliary objectives, and why some routers collapse while others don't. Thanks for watching. If you're training MOEs at research scale, I hope this saved you some pain. See you in the next one, and don't forget to like and subscribe.